Hello, my name is Ashwin, and I'm joined by Hayden, Frank, Andrew, David, and Ranit. Our project is synthetic data augmentation for bone fracture identification using PSLD, and this is a bounding box problem. So we begin with an introduction and motivation here. As we know, object detection models are data hungry. They require extensive data sets, which are often hard to come by, particularly in medical fields, where the availability of MRI and X-rays is limited. This scarcity is what drives our project. Here's an example on the left of an X-ray where object detection could be used to identify fractures. We have taken on this challenge by employing PSLD, posterior sampling latent diffusion, to augment data sets for object detection. This method not only enriches our data, but also allows us to work with a smaller medical data set and then augment it, turning it into a robust proof of concept. In our comparative study, we've leveraged the latest YOLO V7 technology to identify bone fractures. We examined its performance both with and without the performance of PSLD, as well as comparing it to a naive approach. The results are promising, indicating a path forward for object detection in medical imaging, even when data is scarce.
Given we wanted to focus on medical imaging, we found a dataset of over 1,000 different X-ray fractures. Using our techniques, we doubled the size.
So before we talk about our dataset augmentation techniques, let's talk about the object detector itself that we're going to be using. So of course, we'll be holding this constant throughout the study so that we can see the results of the different dataset augmentations. We wanted to use an object detector that's as new and as accurate as possible, as we want to start from the most accurate that we can get, and then see how much more accurate we can make it with our augmentations. So the object detector that we're going to use is YOLO V7, specifically YOLO V7 E6E, which is the largest version of YOLO V7. It has about 150 million parameters. And it is the most accurate version of YOLO V7. It can achieve about 74% MAP at 50 on MS COCO. So we started with the weights that were trained on COCO and then trained on our bone fracture data set. As a baseline on the data set itself with no modifications, the YOLO V7 E6E achieved 0.715 MAP at 50. This is decent performance. You can see the rest of the training stats there. So this is the baseline from which we can compare our other augmentation methods throughout the experiment. So next, we're going to talk about the naive approach to dataset augmentation, and then we're going to go into our method using PSLD after that, and we'll compare the results of each.
So the naive approach employs straightforward image transformations to increase data variability. These include horizontal flipping, random adjustments to brightness and contrasts, rotations, and strategic cropping, as well as random erasing as well. While this naive approach is less sophisticated than procedural synthetic methods like PSLD, it's a foundational technique that is still accessible and still powerful for enhancing model performance, as indicated by the results. Right, so here are the results for training YOLO on this naive augmented data set with these methods. And as you can see, here's the map, 0.746. As you can see, it helps improve performance of the YOLO, but not as much as the posterior sampling latent diffusion technique, right, in painting that we will talk about.
So the standard naive approaches do improve performance, but not as much as our PSLD method will, as we'll show in a second. Before we get into the details of that, let's talk about some of the other literature and other work that's been done on synthetic data augmentation.
Prior attempts to use latent diffusion models to create augmented data, most of the time they graft the image into the diffusion process. So the diffusion process would just graft part of the target image into the image that we're diffusing up from for just image classification. And so they showed that it worked pretty well. One potential thing that was overlooked and was then later mentioned in another paper is that they're allowing data leakage essentially into their training set. And so if certain images from the internet are basically being essentially recreated by the diffusion model with very little imagination, it can't be really seen as a universal data augmenter. And so it's less effective. But then there's other papers which tried to fix this by using textual inversion to fine-tune the model before doing this grafting process if they're training it on a data set that was likely to have data leakage, they could first remove the ID of that image from the Stable Diffusion model. It was seen to be very, very effective in creating new samples. However, these are all not using inverse techniques, and they are really all also requiring fine tuning, which again is this case of data leakage and really doesn't imply the use of it as a universal augmenter. So yeah, I'll go into a little bit about our approach and how we did augmentation and some of the results that we saw. We would take this image, say the image on the left, and we would apply a mask to it and then feed that mask in to the latent diffusion model and use PSLD to try to reconstruct the image. We have the giant square is the bounding box given to us from YOLO or whatever object detection method you're using. We get something like this, where as you're pretty close to the bounding box, you're more likely to be part of it, but as you walk farther and farther away, you're less likely to be a part of it, which allows the model to hallucinate less when it's closer, but more when it's farther away. A few examples of what this reconstruction looks like is that you can clearly see that towards the bounding box, we have something very, very similar to the original image. But as you walk away, the model begins to hallucinate more and more and add in more stuff. And so we can take a little bit more look at that difference towards the center of the bounding box. We can see that there is some of these pixel variations. As you walk away, these black spots indicate large differences in the pixels. We ran the results to the training, so we did the naive augmentation techniques talked about. We compared it to a baseline, which was just our normal training data set, and then we also had the PSLD augmentations on top of it. So for the PSLD augmentations and the naive, we created about 1,000 new samples for each of them. And as we can see, the PSLD augmentations did add significant performance. So this is the validation MAP scores. It did a lot better on the validation, and it did significantly better on the test set. We can see that PSLD does a lot better on the validation and on the test compared to these other techniques. Especially when looking at the test, there's clear improvements for using the PSLD over the baseline and over the naive. Finally, I also want to spend a little bit of time talking about future applications of this work and potential areas that we can really continue this research in. We have this really great idea right here, and it looks like it's working, and it's important to go then apply this to a more substantial data set like Pascal Voc. This is seen as more of a baseline. I would also like to say that a lot of work going into these have been just using Stable Diffusion right out of the box. Well, then we're going to have data leakage, and it doesn't really show that Stable Diffusion can be used as a universal data augmenter. It's important to actually try to correct Stable Diffusion before using it as an augmentation device, preventing data leakage from happening when training on a more substantial data set like Pascal Voc. Another thing to note and another direction is interplaying with the prompt into the training or into the inference time of PSLD. I think it'd also be interesting to maybe test working with ambient diffusion. Curious about how that can be interplayed with the training of these models so that maybe it doesn't learn to just in-paint the exact thing that it's learning, especially if you have these low sample data sets. If you only have 10 samples, it might just overfit when you're fine-tuning the model to those 10 samples. But we could boost those samples up by using ambient diffusion to create a ton of more samples. And I'm curious about the interplay of ambient diffusion and the PSLD, especially when it comes to data augmentation.
So to summarize, on our unmodified dataset, our object detector was able to achieve about 0.715 MAP at 50. Using the naive dataset augmentation techniques that already exist, we could get this up to about 0.74, but by using our PSLD-based synthetic augmentation, we were able to get this up to over 0.78. And using PSLD-based imprinting seems like a promising way to augment and flesh out some of these smaller datasets.